Hello everybody, Namaskar. So in the last 2-3 lectures I have discussed about the simulation of a system, control of a system, measurement of a system. So with respect to those, I should have also discussed about the measurement or measuring instrument for the vapor compression refrigeration system. So that's why in this lecture I will discuss about the measurement or the experimental studies of the vapor compression system with the different instrument which have to be used to measure the different quantities or different operating parameter for the system. Okay, so for the experiment related to the vapor compression system, in general the measurement is made or measurement is done for at the steady state condition. So there are various measurement parameters for a refrigeration system when we will do the experimental study on a vapor compression refrigeration system. So like the refrigerant pressure in both sides or the different state point and the temperature at also various state point of the system. Then we have to measure what is the refrigerant mass flow rate through the system. Then we have to also measure the secondary fluid inlet temperature and also the flow rate of the secondary fluid and outlet of the secondary fluid. So at the different, that means the pressure, temperature, flow rate, these are the some important parameters which we have to measure in case of a experimental study of a vapor compression refrigeration system. Apart from, we can use the energy meter to calculate or to measure the power consumptions for a refrigeration system. We can also measure what is the voltage, we can also measure what is the current. So these are the many parameters we have to measure during the experimental study of a vapor compression system. So by measuring the state point temperature and pressure, we can evaluate what will be the enthalpies at the various state points, and finally based on those enthalpies and mass flow rate of the refrigerant, finally we can calculate what is the cooling capacity of the system, what is the COP of the system. So those parameters, those performance parameters, we can evaluate it based on the measured quantity of the vapor compression system. So that's why for any measurement there are some measured quantity and there are some the evaluated quantities. Okay, so evaluated quantities or those quantities are basically evaluated or calculated based on the measured quantities by using some fundamental equations. Like for this case, the cooling capacity and COP, that can be ultimately evaluated based on the measurement of the temperature and mass flow rate of the refrigerant. Okay, so then I will discuss how we can measure the different quantities and what type of instrument are being used to measure the different quantity for the vapor compression system. So one quantity is the temperature. So temperature is a important operating parameter for any vapor compression refrigeration system. So at the various points, like the various state point of the refrigerant and also the inlet and outlet conditions for the secondary fluid. So for all cases we have to measure the temperature, because the two performance calculation for the vapor compression system, that is very much depending on the temperature measurement at the different state points. So for the temperature measurement of a vapor compression refrigeration system, these are the various type of temperature measurement devices which are used for in the experimental purpose, in the experiment for the vapor compression system. So first widely used sensor or the device is the K-type thermocouple. Okay, so this thermocouple is basically based on the thermoelectricity theory. So that means for the thermocouple, the temperature difference or temperature is converted to the electromagnetic force, that is the voltage. So that means by measuring the voltage for some temperature, we can evaluate what is the temperature at some points. Okay, so these thermocouples are widely used in many measurement of the vapor compression systems. So this K-type thermocouple, there are many type of thermocouple, but within that K-type thermocouple is mostly used. So for this case, your approximate temperature range is minus 200 degrees centigrade to the 1260 degrees centigrade. Accuracy is approximately 1.1 degrees centigrade to the 2.2 degrees centigrade, or the 0.4 to 0.75 of the reading. So whichever is greater. So apart from the K-type thermocouple, the another devices, that is the resistance temperature devices. So resistance temperature devices or resistance temperature detector, that is called also called the RTD. So RTD sensor, in the RTD sensor, for this case basically based on the temperature of a state point, your resistance will be changed. So for this case basically we will measure the resistance depending on the temperature at some point, and from the resistance ultimately we will evaluate what will be the temperature at this point. So we should know the variation in between the temperature and resistance. So for the resistance the resistance RTD. So RTD, that is used for the range from the minus 200 degrees centigrade to approximately 850 degrees centigrade, and for this case accuracy is better as compared to thermocouple. So this accuracy is 0.03 degrees centigrade to the 0.3 degrees centigrade at the 0 degrees centigrade. So for the resistance RTD sensor, measuring range is slightly lower as compared to thermocouple, but the accuracy of this RTD, that is very much higher as compared to the K-type thermocouple. Then another sensor which is called the resistor. Okay, resistor is basically also based on the measurement of the resistance. Okay, so basically the RTD and resistor both are basically related to the temperature measurement with temperature measurement by the measuring of the resistance. So that means for both cases the behavioral change in between the temperature and the resistance, that is very important. So for both cases basically resistance is measured, and based on that resistance we will evaluate what is the temperature. But the basic difference in between the RT and resistor is that although both are depending on the resistance or resistance based temperature measurement device, but in case of RTD we will use the pure metal. Okay, pure metal, and for the pure metal, by using the pure metal we will measure the resistance. But in case of resistors we will use the alloys or the semiconductor. Okay, so semiconductor is used in case of thermistor and pure metal is used in case of the RTD, and some other differences like in case of RTD the variation or relationship in between the resistance and the temperature, that is linear, but in case of thermistor the resistance and temperature are a nonlinear function. Okay, so that means the variation in between the resistance and temperature, that variation is nonlinear in case of thermistor. Okay, and also in case of thermistor again your the temperature range with the thermistor, that will be much lower as compared to the RTD, but the accuracy in case of thermistor, that will be again higher as compared to the RTD. So for this case the that a range we can use -100 to +300 degrees centigrade, and accuracy is approximately 0.4 to 0.1 to 0.2 degrees centigrade in case of transistor. Okay, so basically the K-type thermocouple, resistance, RTD and thermistor, all three are basically contact type temperature measuring devices. So but some cases if you want to use the non-contact type temperature measurement devices, so for that case we can use the infrared sensor or infrared camera to measure the temperature. So for this case, basically this temperature measurement, for this case we can measure or estimate the temperature at some place based on the infrared radiation in between your sensor and that location where you want to measure the temperature. So this is a non-contact type temperature measurement devices, and this type of devices or infrared camera, infrared sensor that we can use for the range from -30 degrees centigrade to the 1200 degrees centigrade, and accuracy is approximately 0.5 to 2 degrees centigrade. Okay, so these are some temperature measurement devices which can be used for the refrigeration applications. Then other instrument, important instrument or important parameter, that is the pressure. So we have to measure the pressure at the different point, so that we can also measure what is the pressure drop for some heat exchanger. So the pressure measurement that we can do, or for this case we can use the different type of sensors or different type of device to measure the pressure. So these I am listing some of the sensors or pressure measurement devices which are frequently used in case of refrigeration system. So first one is the Bourdon pressure gauge. So that Bourdon pressure gauge, that will basically give the gauge pressure. So this pressure gauge or dial gauge, okay, that is widely used in the refrigeration application. So for this Bourdon gauge or dial gauge, the pressure measuring range, that is 0.6 to 700 bar, and accuracy is about the 1% to 2% of the full scale. Apart from this, we can use the manometer pressure gauge. So for the manometer pressure gauge, the range is approximately 0.1 to 2 bar, and accuracy is approximately 0.1% to 0.5% of the full scale. Then apart from this, we can use the piezoelectric pressure sensor. Okay, so this piezoelectric pressure sensors, for this case basically we are measuring the voltage, okay, or electrical properties. So electrical properties that will be changed due to the change of the pressure or change of the stress. Okay, so by using the piezoelectric pressure sensor, we will basically measure what is the voltage. So that means for the given pressure, there some stress will develop, and that stress will change the electrical properties, and we can measure the voltage for that case, and by using the measured voltage, we can estimate what will be the pressure. Okay, so similarly for other type of device which is called the electromagnetic sensor. So for this case also, actually if the pressure will change, then the magnetic displacements will be there, and if you measure the magnetic displacements, and based on that we can estimate what is the pressure. So electromagnetic sensor is also one sensor which can be used for the pressure measurement, and for this case range is approximately 0.14 to 15,000 bar, and accuracy is approximately 0.05% to 0.5% for the full scale. So apart from the pressure and temperature, another important measurement parameter, that is the flow rate, okay, mass flow rate of the refrigerant. So that For that case, we have to use some device which will measure the flow rate. So for in case of flow rate, that flow rate may be the volume flow rate or maybe the mass flow rate. So if we measure the volume flow rate, so then we can evaluate what is the mass flow rate if the density is known to you. Even some measurement devices, related measurement devices, that can also measure the velocity. So if you know the area and if you measure the velocity, and based on that we can calculate what is the flow rate, volume flow rate, and if you know the density, then we can also estimate what is the mass flow rate. So there are various flow measurement devices. So some devices can measure the velocity, some devices can be used to measure the volume flow rate, and some devices may be used to measuring the mass flow rate. Okay, so I have listed some of the flow rate measurement devices. So one is the rotameter. So the rotameter is most simple type flow measurement devices, but using the rotameter we can measure only the volume flow rate. Okay, so volume flow rate can be measured by using the rotameter. So for this case, the range, this can be used in a wide range, so like the 10 to the minus 3 to 10 to the 3 liter per minute. LPM is the liter per minute. Similarly, another type of devices, that is called the turbine meter. So this also used to measure the flow rate. So but for this case the range is slightly higher. So for this case also the range may be 10 to the minus 3 to 15 into 10 to the power 3. So the higher range or the turbine meter is preferably used for the high volume flow rate. Then apart from this, we can use the vortex meter. So for this case also we can measure the volume flow rate, and for this range is from the 50 to 900 LPM, liter per minute. So apart from this, there is a Coriolis meter or Coriolis mass flow meter. So but interestingly, the Coriolis mass flow meter, that is based on the Coriolis effect when the flow is occurs through some bend section. So for this Coriolis mass flow meter is used to measure the mass flow rate, not volume flow rate. So we can directly measure the mass flow rate by using the Coriolis meter. So for this case, the range we can use, that may be the from few gram per hour to the 4 into 10 to the 6 kg per hour. Okay, so in case of wide range, to measure the mass flow rate, we can use the Coriolis meter. Apart from this, we can also use the ultrasonic meter. Okay, so the ultrasonic meter, for this case there is basically the interrelation in between the ultrasonic and the flow rate. Then apart from this, we can also use the electromagnetic meter. So this also used for the volume flow rate measurement. So for the ultrasonic meter or ultrasonic volume flow meter, for this case range is approximately 0.5 to 33,000 liter per minute. Then for in case of electromagnetic flow meter, for this case that range also from the range is from 0 to 10 to the power 5 liter per minute. Okay, so apart from the volume flow rate, we can also measure the dryness fraction of a refrigerant, because in case of vapor compression system, the various at the various position of the system, there may be the evaporation and there may be the condensation. So during the condensation and evaporation process, at the some state point may be in a two-phase zone. Okay, so that means for the theoretical analysis, we have assumed that the evaporator outlet is a saturated vapor and the condenser outlet is a saturated liquid, but sometime the evaporator outlet may be in a two-phase zone. So that means both the liquid and vapor are there. So for that case the dryness fraction measurement is very important for that case. Similarly, some cases may be like that the outlet condition of the condenser is not saturated liquid, that is in a two-phase zone. So that means for that case also we need to measure what is the dryness fraction at that condition. So another reason for the measurement of the dryness fraction is that in conventional setup, basically we are using the rotameter to measure the volume flow rate of a refrigerant, and then we will measure the volume flow rate of refrigerant, and then we will multiply, we know the pressure and temperature. So based on that we can get what is the density at that point. So by the measuring the volume flow rate we can multiply the density to get the mass flow rate. Okay, but if that is a single phase, so by measuring pressure and temperature we can easily estimate what is the density at that pressure and temperature. Okay, but if the condition is in a two phase, so for the two phase pressure and temperature are independent. So that means by measuring pressure and temperature we will not able to estimate what is the resultant density of the mixture. Okay, so that means to get the density and to get the density of that mixture, that means the solid liquid vapor mixture, we need to know what is the fraction of liquid and what is the fraction of vapor. That means we have to know what is the dryness fraction at that condition. So by using the dryness fraction then we can estimate what is the resultant density, and then we can get the actual mass flow rate by measuring the flow rate at that condition. Okay, so that's why if you use the rotameter, simple rotameter, then if you use that rotameter after the condenser, then if the outlet condition of the condenser is not saturated or single phase condition, then for that case we can get the volume flow rate, but for the mass flow rate we cannot evaluate it without the measuring the dryness fraction at that condition. But by default if we assume that that condition is the wet saturated, that means the saturated liquid, and if you use the density to calculate the mass flow rate, so that answer will be not correct. So that means we will get the incorrect mass flow rate by using the rotameter. Okay, so obviously if you use the devices like that vortex tube or the Coriolis mass flow meter. So if you use the Coriolis mass flow meter, for that case we can directly measure the mass flow rate. Okay, so for that is okay. But if you measure the volume flow rate, then if you want to evaluate what is the mass flow rate, so for that case if the condition is the two phase condition, so dryness fraction values also you need to know to get the accurate estimation of the mass flow rate. So that's why in some cases the dryness fraction measurement is also very important. So for the dryness fraction measurement, that procedure is not so simple. This is slightly complicated procedure to how you can measure the dryness fraction. So in many system or many application this type of measurement option is there. So we can use the tomography, so electrical capacitance tomography, ETC. So this type of methods is generally used to measure the dryness fraction of that refrigerant at that condition. So for that case what basically we will do, we will basically the dielectric permeability distribution, that interior dielectric permeability distribution you have to first finding out. So and that by using the external capacitance measurement. Okay, so basically we will measure what is the distribution of the liquid inside the vapor, or what is the vapor and liquid distribution, and based on that the liquid and vapor that will have the defined capacitance. So that's why based on that if you measure what is the capacitance, and so that means that will give the dielectric permeability distribution over this. Okay, so by measuring this distribution, ultimately we have to get the capacitance, and that then we can interpolate in between the solid and vapor portion. So that's why ultimately we will get the liquid and vapor. So ultimately we will able to measure the what is the distribution of the liquid and vapor. Okay, so from the distribution of the liquid and vapor, ultimately we can estimate what is the fraction of vapor in that mixture. Okay, so based on that, ultimately we can calculate what is the dryness fraction, okay, of that steam or at that condition. So this is the one procedure which can be used to measure the dryness fraction of a refrigerant in the vapor compression refrigeration system at the two-phase condition. Okay, so let's say one example we can consider how we can use the defined measurement procedure, and ultimately we have to evaluate what is your performance parameter for that system. So I am taking example of the water cooling system. So two type of water cooling system. One is the non-flow type water cooling system. That means the water is cooled and that is stored, and we can take the water as our requirement. So in general, in case of the household water cooler, so for all the cases that household water cooler is basically the non-flow type water cooling system. That means for in case of water there is no flow. So for that case is basically that evaporator coil that is merged inside a container, and that container is contains the water. Okay, and that water is cooling, and that is basically the basic feature or the construction of the household water cooler. So if you want to measure or estimate what is the performance of this system, so we can make the measurement by this way, that if you start the system, then before starting you have to measure what is the initial water temperature and what is the initial electricity reading. Now after some time, after the starting of the system, after some time, again you have to measure what is the water temperature and what is the electricity reading. So within that time we can measure what is the electricity consumptions and what is the water temperature change during this period. So if you know the volume of the water and if you know the heat capacity of the water, so that means we can calculate what is the refrigeration capacity within that time. Okay, so that refrigeration capacity or water heat rejection or water heat change. Okay, so mass of the water into the heat capacity, specific heat capacity of the water, and the temperature change. So that amount of heat is basically the subtracted from the water. So that is basically cooling capacity. That cooling capacity divided by the electricity consumption during that period, that will give the actual COP for that system. Okay, so in case of the flow water cooling system, so for this case the water is flowing through the evaporator with a certain mass flow rate, and for this case you have to measure the inlet temperature, you have to measure the outlet temperature, you have to measure what is the mass flow rate of the water, so that we can measure what is the cooling capacity for the water cooler, and also we have to measure what is the electricity consumptions or electricity consumptions rate. So the actual cooling capacity by the electricity consumptions rate, that ratio will give the actual COP for this type of water cooler. Okay, similarly the air conditioning application, you have to if you want to estimate what is the performance. So for that case also the air inlet condition and air outlet conditions, like the air inlet temperature, air inlet humidity, similarly the outer evaporator outlet air temperature, outlet air humidity, and also the air flow rate and the electricity consumption rate. These are the some parameter you have to measure, and based on that you can evaluate what is the actual COP for this air conditioning system. Thank you.